try to cry loudly.
It's an honor and a pleasure for me to give a talk at this seminar. I would like to thank organizers for this opportunity. I'm going to talk about automorphisms of complex non-Kähler manifolds. These manifolds are given by their construction, which is analogous to their construction, to the well-known construction of quotient construction of toric varieties due to Batyrev and Cox. This manifolds provide, this construction provides quite a wide class of non-Kähler compact manifolds, including, for example, such examples as Calabi-Eckmann manifolds, and Hopf manifolds. Calabi-Eckmann manifolds have the following form. Topologically, they are just products of dimensional spheres. And they are equipped with this product will be equipped with some complex structures, and they form each forms a principal bundle over the product of projective spaces. With fiber torus. Now, if we have a product of projections of odd number of projective spaces, odd number is odd. If we have such a product, we may take a Hopf principal bundle over each projective space, and then equip it with some complex structure.
Let me ask some questions. So let us consider complex affine space, right? This is even dimensional real space. So it contains odd dimensional unit sphere, right?
Yes.
So it's project this complex affine space. If you omit origin, then it projects to complex projective space.
Right.
And you restrict this map to the unit sphere, right?
Yes, and in this manner we obtain the Hopf principal. With fiber, okay, the fiber is circle.
By torus, you mean not what do we mean? You mean a real torus.
Yes, you have a real torus here. Here is really torus, which is product of L circles, and here L is odd. Therefore, we make this complex structure, and it may be.
Sorry, I don't understand. If L is odd, then this S1 power L is an odd dimensional real variety.
Yes.
So no complex structure is possible, right? Because this is an odd dimension.
So it's confused the word. It's even, and you have it's an even dimensional real variety, real manifold. And it is possible to choose some complex structure here and obtain a complex structure on the products of on the fiber, right? And we may obtain a complex structure on the whole total space. It's effective. It's possible.
And this projection, this is component-wise. So nothing diagonal, right? This is a direct product of projections. And who is Calabi-Eckmann and who is Hopf in this picture?
First, now I'm talking about Calabi-Eckmann. Hopf, I'm going to tell about Hopf manifolds right now. I like to notice that among this family of such a manifold that forms a total space of principal fiber bundle over the product of projective lines with fiber a torus of complex dimension 1. It is the most classical
No. Just a moment. Please erase this T1. Right? That this is S1 times S1. Okay, usually by T1 we mean algebraic torus. So this is a compact torus.
And Hopf manifolds are obtained by following construction. Take and have a fine complex space, remove 0, and take a quotient by action of a group. This is isomorphic to integer numbers, and this action is generated by an operator with whose eigenvalues are all greater than 1. And this quotient is isomorphic to the product of spheres. It is easy to see from topological considerations that these classes consist of non-Kähler manifolds, since the second cohomology groups are 0.
Misha, let me ask. So, take any matrix, complex non-degenerate matrix, whose eigenvalues have absolute value bigger than 1, okay?
Yes.
So you claim that if we generate a cyclic group by this complex matrix, then the quotient of Cn minus 0 will be always the product of two spheres.
Yes.
It doesn't depend on this matrix U.
It doesn't.
Is it possible to understand it somehow?
I guess it's not quite easy to see, but let me demonstrate it on a simpler example, like this. We take a quotient of C2 about 0. We have, for example, by a diagonal matrix.
Okay.
We take here, S3, and we contract we have following representation of the space. And when we contract this, taking the quotient, we obtain, it's to see that we obtain manifolds the following form. I guess.
No, I don't understand. Okay, C2 minus 0 is a product of three-dimensional sphere and one copy of real numbers.
Right.
It's not real numbers, it's greater than 0.
Just different values of radius of the spheres. Okay, clear. And now how do you understand that quotient is this?
Okay, I draw a picture. Spheres here of different radius, and we applying this operator, we take the quotient. You see that if we have here a unit circle, here a circle of radius, a sphere of radius 2, and we
So just basically take the quotient of positive real numbers by a subgroup generated by 2.
in fact, yes, we have a quotient of positive real numbers by a subset. Yes.
Can you draw positive real numbers and mark this powers of 2? And also small powers of 2. And the quotient is somehow a segment with gluing together ends, right? So your group, it acts on the set of spheres, and set of spheres is this array. And action of the cyclic group on this array has a quotient circle. So you have one sphere times this circle.
If we take a general case, when the operator is not scalar, then we have a unit sphere. We act, and its images are non-intersecting spheres, up and scale down uses. And the fundamental domain is this region between two spheres, I guess.
Yes.
Okay.
Fundamental. It's
You can, it's the one this.
and we glue together. It's.
But who is Hopf? Hopf, this is morphism.
Hopf
And who is Hopf as a manifold? Just product of two spheres?
Product of two spheres with complex structure arising from this quotient.
This quotient construction allows you to descend complex structure from upstairs downstairs. Why? Because this is a local isomorphism.
It's discrete group action. Covers by
Yes, it's. The effect is more general fact actually that if we have some complex manifolds and proper discontinued action of the group, then the quotient is and free. Actually, then the quotient is equipped with a structure of smooth complex manifolds.
You can cover each point with a neighborhood which does not intersect its images, and thus you obtain complex structure of the world.
So this is not the principal points of my talk. These are just some examples.
Okay, but very last question. So Calabi-Eckmann, this is a product of projective spaces. Eckmann. They have already complex structure.
Yes, but we consider this is these are manifolds, and it's just convenient to keep in mind that therefore this manifold is a total space of principal bundle over the product of projective spaces, and it is constructed taking some actually taking the product of projective spaces, then taking actually we may take not the Hopf bundle, but any other principal bundle with fiber with structure group circle, and then we can glue together. We take a product and then some complex structure on the fiber, and
I can understand. In this first case, do we have some exotic or some new complex structure somewhere?
Some new complex structure. We obtain a complex structure on the product of even number of one-dimensional spheres.
Which way? We somehow, in this case, we lift complex structure.
We have complex structure on the base space and in the fiber. And it is possible in this case to endow the total space with complex structure.
And which complex structure do you take on fibers?
We may take an arbitrary.
Because there are many complex structure, right, on such a compact torus, right? Okay.
Okay, then the construction of moment angle manifolds generalizes these examples, and it is connected to the quotient construction, the construction of toric varieties. Okay. Here is the construction. We take Fn. That is given by a simplification of Fn. That is given by simplification of X on the set consisting of m elements, and the pen lies in some space, real space of dimension n. It is a collection of peripheral cones. We have one-dimensional cones, and we choose vectors. We have m one-dimensional cones, which are called rays, and we choose vectors on each ray.
Can you draw some picture?
Of course.
And where is this A?
We have chosen some vectors since we have no lattice from the beginning. We have no primitive vectors on this, and we just fix them.
And what is a complex K in this case?
In this case, for example, if we enumerate the race, the complex, it's okay. It consists of sets of indices such that the cone generated by corresponding rays is the cone of our frame. And in this example, we have a special complex of the following form. We have drawn the vertices, and the edges are correspond to our cones 1, 2, 3, and etc. Okay. Well, since we take we consider only simplification edge, such a set is indeed a simplification complex in the sense that for any subset of a set lying in our complex, any subset of a set lying in our complex is also a set lying in the complex. For example, if we take such a cone
This is not simplicial, right?
This is not simplicial since we have a set 1, 2, 3, 4 such that the corresponding rays generates a cone, and for a subset, for any subset of consisting of 3 elements, for example 1, 2, 3, the corresponding cone generated by this rays is not a cone of the effect. The effect consists only from this cone and its faces. Okay. And we also need this fan to be complete. This means that if we take the union of cones lying in the fan as subspaces of Rn, we obtain a whole space. So, given this data, we may construct the following space. Let's say Cn, and remove a configuration of coordinate subspaces which is the configuration is given by the combinatorics of the pen. It may be represented in the following form also. It's the set of points of Cn such that the set of indices such as the corresponding coordinates are 0 lies in the special context. This is the space that is used in the Batyrev construction of toric varieties. Then we consider an action. First, to describe the action, we need some notation. We denote by A the linear map that from Rm to Rm, the space where our pen lies, that sends a vector of standard basis to the chosen vector on the array with corresponding number. Okay, since our pen is complete, it's calls necessarily that m is greater than n, and we have a kernel. We will denote the space by V. Now we will need the construction of Gale reality to construct the action. So I'm giving the reality. Here we have our map A. It's really convenient to denote the space Rn by W star. It is subjective. We have a kernel, which is denoted by V. And we consider the dual sequence, which is exact. And here we have a dual map, which is given by it sends W to M parents with our vectors of A1, and the map which is obtained this place, this position, is provides us M vectors in the space V star, which are given by taken images of phases of standard basis. So the configuration of these vectors is called the Gale configuration. The main property which will be important for us is that the kernel is given now from this exact sequence. We see that the kernel is given by the image of B under the map due to gamma. fact, we are going to act on this space by a subset of, that's denoted by sigma, the following subset. We take the kernel, line in Rm, take coordinate-wise exponents, and we obtain a subset of R positive in power n, which lies in the algebraic torus. And we act by these elements of algebraic torus. But it is more convenient to consider not some subspace, but an adset space whose embedding into torus is non-torus. So we have R sigma is exponent of gamma star of V. So we act by V. The theorem by Hopf and Stanovsky states that this action is free, proper, and endows the quotient with the structure of compact, smooth, real manifolds. And this manifold is holomorphic to the moment n complex. I'm going to tell the definition. So this is a smooth manifold. So this is the principal object of the study in toric topology. And it is defined the following way. We take, let us denote by D2 the subset of complex numbers, such with module not greater than 1. S1 is its not border, but what do you recall how to say then it's
Boundary.
boundary. So it's boundary. And the moment angle complex is given as the following subset. We take the disk to the power m, where m is we have our solution complex on the set of consisting of m elements, and we allow the coordinates to be less than by absolutely less than units. This subset lies in the sufficient place. So it is similar. The definition is similar to the following. And in fact, these spaces are homotopically equivalent in K and ZK. The homotopy equivalence is given by contracting this action, since it's just it's easy to see that this B group is isomorphic to R to the power n minus n. Okay, so this object, which is important for toric topology, is now in case when case in complex of some fan is equipped with structure of smooth manifold.
Maybe for people to understand, can you draw this triangle? So you have this open subset, algebraic open subset in the affine space. You obtain this is an intermediate step, and finally you obtain the toric variety as a call.
I'm going to show it later. Okay.
Shouldn't there be equal to 1 or less than
What should be equal to 1?
1 in the definition of ZK?
Less. Here we have less than.
Does it look like
This is when it is later equal to 1, and boundary when it is equal to 1.
yes, but in the definition of UC of K, it's like different.
It's different, it's not the same, but actually being less than 1 by considering it
It should like correspond to being non-zero, right?
no, we have here the pair of spaces if is the following. We have C and C without 0.
Oh, okay.
So
it's not quite.
analogy is the following. In topological situation, you have pair disk boundary, and in complex setting, you have pair complex space, punctured complex space with 0 removed. Complex line and punctured complex.
Yes, and here complement to C without 0 is just 0. As here, the complement to the circle is a set of elements with x value less than 1. And this manifold, so the manifold we just obtained, it has dimension, real dimension m plus n, and if it is even, we may obtain a complex structure using some additional data.
And what you erase are particular cases of this construction, or not?
Yes, what I raised, these examples maybe these manifolds may be obtained by this construction. I'm going to show it on the example of Calabi-Eckmann manifolds. But first, I want to give the construction of complex structure. If B is even dimension, it has dimension m minus n, real dimension. If n plus n is odd or is even, this dimension of zk, then m minus n is also even, and we write like this, and it's maybe good to do some complex structure later. Then we consider the complexification of V, and it is represented as the sum of two subspaces corresponding to which are the eigenspaces of the complexified operator of complex structure. We have an operator JC acting on the classification of V, and it has two eigenvalues, I and minus I, and this is how we denote the corresponding subspaces. So we are going to act by this space. Actually act by V, but the other this space we take the isomorphism. We have complete structure here, and we have, of course, complete structure on this subspace. The isomorphism is given by the following formula. Then it is embedded into BC, and we consider the complexified action of V. Actually, the action of V was given by the formula of this form. It is seen from this formula. We act by the kernel, by the exponent, which are exponents coordinate-wise. And the kernel is given by as the image of V under gamma star. Here it is this image in the bounds. Okay, this is the action of V. The action of V complexified is given by the formula. We just take projects complexified with some things plus I gamma 1 V, etc. Gamma 1 U plus I gamma 1 V or gamma M. This is the action of V complexified, and as we take embed V into V complexified through subspace, we obtain the following action. We act by V, by this we take coordinate-wise multiplication by these elements of algebraic torus. U minus I number 1 J G.
Mikhail, I know that mathematics is some complicated formulas, but maybe you will obtain us the plan. So what happens?
Okay, I've finished actually.
Complicated formula. Okay.
We obtain a modified action of V, and this action it turns out to be better in the sense of complex structure. We have the following. The action may be represented in this form, and this is holomorphic. So we obtain, and it turns out to be free and proper, and a theorem by powerful Wyszynowski states that in this manner we obtain now a complex structure. So let us denote the group of such elements by H. H is exponent of gamma star complexified of V1, 0. This group is given by this action, and the quotient is deformative to the quotient by the group R, and homomorphic to ZK. So we obtain complex manifolds, complex manifolds, which are topologically non-angle complexes. And it's important to say that if we consider the action of the whole complexified space, let us denote by G sigma the corresponding subgroup in the algebraic torus. Will give us toric variety corresponding to the pen. In the case, okay, I forgot to say that to discuss this, we need the pen to be a pen, actually a pen of atomic elements. It means that a smooth toric variety. It means that if we consider the lattice a subgroup generated by the vectors on the rays, it turns out to be discrete, and actually it is a lattice in the space where the pen lies, and the vectors, if we start from the construction part no lattice, we construct a lattice in this way, and if the vectors turn out to be primitive in this lattice, then it is a pair of toric variety, and if it is additionally regular, then we have a smooth toric variety. And this is exactly the Batyrev and Cox function. This is this holds, the thing is conservation. This is a construction by using Batyrev. So we have indeed such a triangle. Here we take a quotient by H, here by G, and here we factorize by a quotient. Let us notice that this group is isomorphic to C to the power L. L is n minus n divided by 2. This is isomorphic to this algebraic torus of dimension n minus n. And as we take the quotient group, it turns out to be it turns out to be torus, compact torus of dimension L.
But even for Cox construction, for complete simplicial toric varieties, the group where you take this vertical factor, vertical quotient, this is not always torus. It's maybe a disconnected group.
Sorry, could you repeat?
If you restrict your attention only to complete simplicial toric varieties, you have this Cox construction. You realize them as a quotient by some open subset inside of the affine space. And you claim that this group by which you take a quotient, this is always a torus.
The variety is taken to be smooth. Then it is a torus.
If it is additionally smooth, then it is torus. Okay. Can you give us one example of this triangular diagram?
We take a 10 of CP1 times CP1 of a toric variety, so we have here these vectors. And then we consider the kernel A is given by the following matrix. This is 1, 2, 3, 4. Following matrix. The kernel consists of elements of the following form. If we take the quotient by its exponent, we have the following. Its exponent is following form. It's easy to see that the space, I should have first described the space on which we are acting. Use k, just c about 0 times c about 0. And if we take such a quotient, we obtain that's the product of C2. We obtain a product of two three-dimensional spheres. This is what we obtain topological level. But we may introduce some complex structure on this space. For example, let's denote it. We have here x and y just denoted by two numbers. For example, like this, minus y x, and we will obtain for this structure we will obtain okay, this is necessarily like this. We may choose any structure on two-dimensional space, any complex structure, and we will obtain the same space but with a complex structure. And if we take a big group, it consists of elements consisting which are exponents of the complexified kernel. It's easy to see that this is just such elements. Z and W are 0. And we obtain CP1 times CP1 taking the quotient of UK by GC. an example, it will be important for us further when we talk about automorphisms.
Okay, so conclusion is that all of us know Cox realization of toric varieties. This is this quotient construction. So the idea is to consider some intermediate step, which is in general not algebraic, right? And this intermediate quotient space, this is this moment angle complex. And you will compute the automorphic group of this moment angle complex, but under specific situation when it is a complex analytic variety, right? Something like this.
Yes, of course, it's important that we have a complex manifold, and we consider biholomorphic automorphic.
So automorphic group as a complex variety.
Yes.
Okay.
It's very important to say that.
So say in this your example, this moment angle complex is this product of two spheres.
Yes.
And what is the automorphic group in this case? Can you tell us?
Yes, in this case, it's just the product of two quotient by C.
And how does this GL2C acts on sphere?
It acts, we have an action on UCK, it is represented in this case as
C2 minus 0, certainly GLN acts on this Cn minus 0. Okay?
natural action, and it may be lifted, it may be descended to our S3 times 3, but it, this S3 times 3, it is not embedded in the most natural way as from here and from here. It is embedded somehow complicated.
So this first factor, this first GL2, it doesn't act on the first sphere, no?
Yes, it does.
So this is some more complicated action on the product.
It is somehow twisted.
Okay. 20 minutes.
So, I've said it already that K, this complex moment and manifolds is a total space of a principal bundle of toric variety with fiber torus, complex torus. It has complex dimension n. Here is the result. Talk is the description of automorphisms of ZK. We have the following exact sequence to the sequences. This is the normalizer of H in the group of automorphisms of UCK. It is obvious that such automorphisms may be descended to the quotient. So it can be just a quotient of UCK by H. The section is normalized and we will descend. And there is a description of centralizer also, of the unit complement.
Maybe if you have another fancy.
Is it possible to see this line? Here's the unit complement. Here is the normalizer. The bottom line was actually was a correct proof an article by Tema. We had some mistakes concerning the upper line, but this result maybe falls to it belongs to Korea, and this is what I have obtained.
So what are you going to do to prove this theorem?
No, I just have no time for it. I'm going to, I have not completed the statement yet. Let me do it. It's begin to say a bit more about these terms. So the centralizer of H, it turned out to be coincides with the centralizer of a greater group. And the centralizer normalizer then lies, as we write it shortly, I guess we know ambiguity. It lies between centralizer of G and centralizer and normalizer of G. These terms are described, are well known. They describe the automorphisms of toric variety. This term is generated by a torus and root subgroups corresponding to the Mazur roots, and this normalizer is obtained by aiding automorphisms that correspond to the symmetries of the pen. Actually, in fact, the quotient is a quotient of a group of automorphisms of 10. This automorphism gives an automorphism of UCK. We just permute the race and permute the coordinates in UCK in a corresponding way, and this actually descends to the toric variety, but we need to take a quotient by this way, by automorphisms of 10 that give rise to automorphisms of the class group, or in smooth case, the car group, that are trivial. Some ordinals of 10 act trivial on the Picard group. For example, in this case, if we switch, if we permute this to race and these two, this is some more automorphisms is given by it's a linear automorphism of this space, which is just minus, and the pen maps to itself, but its rays are permitted. But this action, it's acts only on it acts on the terms of this project on each term. Yes, we have actually an automorphism here and automorphism here. And,
something is strange. Look, upstairs, GL2 acts on each component. Downstairs, it also acts on each component. But you claim that on the intermediate step, they act somehow still.
Yes, but now I'm talking about automorphism of terms. Yes, we just take portions from I understand that that's too much about this. So, and we have the component group of a group of automorphisms of ZK is represented by this quotient, and it is embedded in the quotient for in the component group for toric variety. Particularly is finite. Is this one. And so there is a way to distinguish this normalizer. Actually, we just take note all the symmetries of the pen, and it is possible to say which symmetry gives rise to an automorphism that can, and which does not.
So the centralizer on the left is basically the identity component of the automorphism group of the toric variety, and the normalizer on the right is the whole automorphism group of the toric variety.
But we need to take a quotient by the torus G. But yes, the whole group for toric variety is like this, and unity component is. Could you repeat your question?
Yes, that's what I said. And how can we describe then this normalizer in between in these terms?
It is generated by a centralizer of G and some symmetries of them.
Okay.
We just need this symmetry of them. Some mechanism for drawing. Here we have a symmetry here as our fan, and each symmetry of the fan is maybe restricted to the terminal. And here we have a complex structure. We just need this linear operator to be C-linear with respect to our complex structure introduced here. And let me show it on this example.
Optimally 10 minutes.
For Calabi-Eckmann manifold, we have the following. It is more convenient to not to restrict the symmetry of the pen, but to pass to the dual sequence. We have Data and we start. It is possible to see that what is due to the space in which determines. It is a group of characters multiplied by R is a character, and this is a star, and here we have we see that there is a singular sequence that describes the Picard. It's complete. We have example sequence, and this is just the Picard group multiplied by R. And here we have a map that here is a map that sends a divisor corresponding to array to its class. So it's gone. And it is more convenient to consider this picture. We have a complex structure on V, so we have a dual complex structure on this star. If we have some automorphisms of a fan, of our fan, like this, it just permutes the coordinates in Rn. It is restricted to the kernel, and we obtain the action dual operator on the Picard group multiplied by R. And it turns out to be just the action of our automorphism. Here's an automorphism of fan, and let us denote by phi sigma the corresponding automorphisms for X sigma of the top variety. And it's just the automorphism, the action of this automorphism on in the Picard times. Our condition that automorphism is this operator is cylinder is translated here in same condition that this automorphism, this operator is cylinder with respect to the dual structure. So in our example, X sigma is CP1 times CP1. What are the automorphisms of the fan? It is the hydra group, and it is generated by an operator by the rotation and by symmetry. You see that symmetries give rise to trivial automorphisms in the Picard. And so we just need to consider the rotation. Rotation changes the classes in the Picard. So this is the only automorphism that may give us some automorphisms in the group of components. Here it consists of one element, and we need to see if it gives rise to, it may be lifted to UCK, and we just need to see if it fixes the group H, if it's normalized. Perhaps for this example, it's not what we actually needed. It is easier to consider it explicitly. Here is the automorphism as we lift it to UCK, let it be noted like this. It just permutes the factors. The same is its action when we consider the conjugation. Consider the conjugation of H. We just compute its coordinates in this way. But let us take some H that fits in our construction. G here just looks like this, and H may be represented as follows. Choosing complex structure on the kernel is the same as choosing a subspace in a complexified kernel that maps to the kernel isomorphically as we take the real part. So we just lift it, somehow twist it so that after taking the real part we have it's the same as how is it done? Our kernel is two-dimensional, so we need to choose some one-dimensional complex subspace in the kernel, in a complexified kernel. Here, let us imagine that these numbers are complex, and how does how may this subspace look? It looks like this: Z, Z, alpha Z, and alpha needs to be not real. In this case, this projection will be an isomorphic. And we take exponents, and here is our group H. And let us permute its coordinates. We obtain alpha z, then z, and then what? It is more convenient to consider its algebra. So we have alpha z, and just to permute, we obtain another algebra. It may be represented as follows. Inverse. It's not the same. And we see that the only automorphism that could have given us an automorphism in the component group does not lie in the units component. Not check this not like this, but okay, it does not give rise to an automorphism of zk since it does not normalize the group H. So in this case of Calabi-Eckmann manifolds, S3 times S3, the automorphism group turns out to coincide with just the centralizer of G, which is 02 times 02, but it is, as we see here, it takes pushed by H, which is isomorphic to C. And we have the same picture for any choice of complex structure. For an arbitrary alpha, we don't have an automorphism in a discrete part. But there is an example. I have computed another slightly more complicated, for a slightly more complicated manifold, and using the action in the Picard group multiplied by R, it is possible to show that for some structures we do have discrete part, and for some there is no discrete part. It's possible to compute the whole automorphism. Okay, I guess that's it. Thank you for your attention. Perhaps you have some questions.
Okay, conclusion. You consider such basic objects like product of spheres, and you describe the automorphism group of the basic object, but I don't know whether a disadvantage or something, but with respect to some specific complex structure on these objects, right?
Yes, this complex structure, there is an important condition that from complex structure we may obtain some vibration. Its vibration should be a total space of the principal boundary. So its fibers should be closed. And in this case we obtain a base space, which is a toric variety. But if we take a slight, deform it slightly, this base space will disappear, and description is not is analogous in this case. But here I could say it's possible to say that we just consider toric varieties and take the total spaces of principal bundles with fiber torus, a torus. and compute automorphic groups of these spaces, not equivariants, of course. And this is the result. But I would like, my goal is to see what happens if we have no toric variety. It is some irrational case. This is a rational case. I say that when it's rational, so we have a toric variety. But if in a rational case, this is big interest for qualitative.
Okay, any more questions or comments? So I still don't understand. In the bottom sequence, you said that centralizer H coincides with centralizer of GC. Yes. And this group of automorphism of UCK, it's automorphism of UCK as a complex manifold. Yes.
UCK is not as what?
As a
complex.
Complex manifold. Yes.
Yes. But it turns out that this centralizer consists only from algebraic automorphism.
So basically, the connected component of identity is the same as for toric varieties.
Yes. Centralizer is the same, but we take quotient by agent.
Quotient. More questions?
This is a result of Young also that these automorphisms, its centralized and normalized age, are all algebraic. My contribution was this subjective. It's made by studying. It's done by studying the topology of this principal boundary.
No more? Okay, so as Shafarevich suggests, let us. Thanks to Mikhail.